All right, thank you all, and thank you all for sticking and making it to the last session. So I'm going to talk a little bit about software verification and my research. And maybe I don't have to tell you this, but in our world, software is everywhere. You can find it, on our phones, in medical equipment, flying airplanes, controlling power plants, and many critical infrastructure. And unfortunately, that also means that software bugs are everywhere. And just to give you some examples, maybe the earliest famous example is the Therac 25 radiation therapy machine, which was deployed in the 80s. It was a great innovation at the time. It saved a lot of time in setup of radiation therapy for cancer, which was done manually. Now it was done mechanically and automatically. But it turns out that it had several software bugs. And this led to some patients receiving even lethal overdoses of radiation, and at least 3 people died due to that bug. And it's famous for one of the first bugs that actually killed people. Another kind of well-known spectacular software bug was in the Ariane 5 space launch, which crashed, I think, 37 seconds after launch because of an integer overflow software bug. And this might sound like, the 80s and the 90s, and haven't we gotten better at constructing software and building correct software? But unfortunately, it's quite the opposite. The software we're building is only becoming more complex and more complicated for various reasons. So I have a couple of recent examples here. Let's see. So 2021, 4 years ago, maybe some of you remember this. This was a big deal, the log4j bug known as log4shell. An open source library that is used really, really widely across the internet, had a bug that allowed attackers to execute malicious code. And this, in the 80s and 90s, we had specialized teams, proprietary software constructing, and kind of an organized effort. Software today is much more complex. A lot of it is using open source software that the people using it don't even bother to read, and don't bother to read the source code of that software, which I don't want to say it as if it's bad. It's a good thing. We can we can construct software much faster now because of this, but it also introduces these risks. And just last year, a big scandal was the CrowdStrike update bug, where an update from this CrowdStrike company caused about 1% of Windows machines worldwide to crash, and it, it shut down air traffic, and it impacted hospitals, and it really impacted a lot of different areas of life. And, to make things even worse from the perspective of the reliability of software, we are now all excited about AI generating software and large language models generating software. And I think it's just a matter of time until we're going to see some high impact bug like that was due to code generated by AI. So I hope we can all agree that this is kind of a big deal. And the question is, what can we do to stop these errors or finding them before we deploy the software? And the main common practice today in industry is testing. So this is kind of an illustration based on a case with the Brooklyn Bridge. After they built it, people were quite hesitant to cross it. So they took elephants from a circus, marched them through the bridge, and everyone trusted the bridge much more. And there is a lot of common sense to that, right? You build some system, you test it maybe on a few inputs or on the extreme inputs where you think it might fail, and if it works, you should trust that it works for all inputs. And that's mostly what we do with software. But there are, of course, a lot of problems with this, and this is a famous quote from Edgar Dijkstra, a famous computer scientist, saying that program testing can be used to show the presence of bugs, but never to show their absence. From testing, you can never be sure that your software doesn't have a bug on an input that you didn't test. So the alternative to this, and we can take inspiration from some other engineering disciplines, is to do a mathematical analysis. For example, now before we construct a bridge, we don't just test it, we design it, and we perform a mathematical calculation of the forces and stresses that it's going to encounter under some reasonable assumptions. And then we have a mathematical reasoning process to conclude that the bridge is going to function as intended. And the idea in my field, the field of formal verification, is to try to do the same thing for software, to analyze it mathematically and to prove that it has no bugs, or at least that it adheres to some formal specification under reasonable assumptions. Now, the dream that we all have in this field is that we would have some magical box, some magical algorithm that would take our system, like our million lines of code for some software, or maybe a few thousands or tens of thousands of lines of code for really important software, and some formal specification of what you want for it. And it could be that it doesn't crash, or it could be something richer, that it really, let's say, delivers the right amount of radiation to the patient. And kind of automatically tell us either the software is correct, or I found a bug, and here is a counterexample. Now, I won't get into the details of this, but there is a theoretical proof that this is impossible. We can never fully automate this process. And for that reason, already I think this is from the 80s or 90s, there is this very pessimistic quote that says that formal methods are the future of computer science, always have been and always will be, that we will never be able to realize this dream of mathematically verifying our software. But we are more optimistic, and we are still trying. So kind of one alternative to this fully automatic approach is to take a manual approach, to have the programmers that build the software also write down a proof, a formal proof that it is correct, and then just have a machine check that proof. And in principle, that you can do that, and there are some success stories of doing that. But the main problem with that is that the picture looks more like this, that the proof that you have to write is so detailed, and it has to cover so many uninteresting details and arguments about your software that it's very tedious, and it creates a lot of effort, and you would have to write somewhere between 10 to 100 lines of proof for every line of code. And that's not very practical for most software. So the main theme of what I'm trying to do in my research is to kind of explore the spectrum between fully automated proofs and fully manual proofs, and find the right balance that would allow us to make software verification more practical. And I'm using several principles for doing that. One is using decidable logics. I'll tell you a little bit more about that. The other is decomposing the problem into several subproblems that some of them might be solvable automatically. And another principle is primal dual algorithms, which are a type of algorithms that have some very nice mathematical structure that I believe can really simplify this problem. So the specific area where most of my work focuses is verification of distributed algorithms and distributed systems. And this area is an excellent opportunity for verification. These systems are very widespread. You can find them on many scales, from the communication between redundant chips that control the brakes of the car, to global scale systems that are used by billions of people. And they all have many challenges of functioning correctly in the presence of communication failures and computer failures. And what's also nice about them is that they are both notoriously hard to get right, and testing does not find all the bugs. And also that algorithm and protocol descriptions are sometimes pretty short. You can sometimes find a description of an algorithm that is maybe a page or two in a paper, and it can contain very subtle errors. One example of this is the Ziziva protocol. It's a distributed protocol originally published in 2007, and it was kind of a big deal. It won the Best Paper Award at this prestigious conference, and it was also followed by a journal version where, of course, it had correctness proofs for all its key properties. But about 10 years after its publication, researchers actually found that it has a bug, and that those proofs were incorrect. Those were just paper proofs peer-reviewed by the community. And this is the kind of errors that my research can detect mostly automatically. And this is not just a problem with theoretical papers. This study, for example, found more than 100 concurrency bugs of this type in deployed systems. So to put my work on verification of distributed systems in context, I want to mention two other projects. Okay, let me skip a little bit because it seems I'm running out of time. Let me skip to over here. So one way to put my research in context is to consider these two axes of expressiveness of the property that we are verifying. versus the level of automation. And there are some approaches that use very little automation and they can verify very complex properties, and other approaches that use much more automation but can express only very limited properties. And the tool I'm building, called Ivy, tries to push this frontier over here to have a little bit less automation but have much more expressiveness and to have really productive interaction with users. This is a table of numbers showing some protocols we verified. And the one I'm really excited about, one of them that I'm really excited about is this stoppable Paxos example, where the authors of this protocol said that it's, although the idea is not complicated, getting the details right was not easy. And the original paper actually included a very detailed proof of correctness with very careful reasoning. And with the techniques that I'm developing, we could actually have a semi-automated proof of this protocol with just 16 lines of manual invariants that the users had to write, and this was all automatically checked in around 5 seconds. So let me conclude. Let's see if this works now. Yes. So we are increasingly using software, and we're increasingly relying on our software to be correct. And formal verification provides an opportunity to increase the reliability of the software we use, but existing approaches require really too much effort for it to be widely applicable. And my research is trying to find a new balance between automation and user interaction to make software verification more practical. Thank you.